One of the concerns I have for tomorrow is at this time of the day we do expect thunderstorms to develop and move into the area very close to the launch pad. And as you can see in the surrounding skies right now, we do have some very large thunderstorms developing, and it's going to be how close those thunderstorms get to the launch pad at the designated launch window and whether or not they'll be violated or not. Now what we use are several pieces of instrumentation. The two main pieces that we use during the countdown will be our weather radar and a weather aircraft that will fly around, fly into these clouds to measure how tall they are and how far away they are, and things of that nature. Well, we have a set of weather rules, roughly 10 to 11 weather rules that were established back in the late 1980s. And what these rules involve are clouds and the potential for these clouds to not only produce lightning on their own, but also what we name triggered lightning, rocket triggered lightning, which is basically as a launch vehicle flies through a cloud, it could trigger its own lightning bolt. If this cloud has certain characteristics, mainly is it big enough, is it high enough, is it over the freezing level? If a rocket flies through it, it could in fact trigger its own lightning strike. It's basically the velocity of the launch vehicle as it's flying through a cloud. It's not necessarily the vehicle itself, it's the speed of the vehicle as it's flying through the cloud that could produce a lightning strike. Florida is the lightning capital of the United States. I think it's second in the world to places in Australia, but it is the lightning capital of the United States. Florida would have to be the hardest place to forecast. I've been to other parts of the country where normally you look to the west and that's where the weather is coming from. In Florida, they can come in all different directions. And they sometimes can come for no reason whatsoever, at least no reason that's apparent to us.
Launch on this project was a lot tougher than I ever expected it to be. Getting to Mars, flying a mission to Mars, is hard. I didn't think that just getting off the ground was going to be the challenge that it actually turned out to be.
You know, the launch is inherently a risky activity. It's one of the higher risk portions of the mission. On top of that, we had some late-breaking changes and repairs we had to make to the spacecraft.
A couple of months before we launched, we blew a fuse on the Spirit spacecraft. Then in the process of evaluating the fuse problem, we found what could have been a very serious flaw in the design of the system on board the spacecraft that fires pyrotechnic devices. And that really had us scared. And there was a lot of work that we needed to do to clear those problems out of the way. And that took us up until really just a few days before it was time to launch. The other thing that slowed us down on Spirit was the weather. That was a daytime launch. In fact, it launched around 2 o'clock in the afternoon, and 2 in the afternoon is, at that time of year in Florida, when thunderstorms come through.
We eventually launched on June 10th, which was basically 12 days into the period. And as a result, we were really under pressure to get Opportunity ready to go.
We tried to launch one night. It was stormy, thunderstorms, lightning out over the Atlantic, and then there was a fishing boat out there. And of course, if you have rockets taking off and dropping solid rocket motors into the ocean, you don't want them landing on fishing boats. So both the weather and the fishing boats would have stopped us that first night. What then happened was we started to run into problems with some thermal insulation on the outside of the rocket.
When we went back to inspect the launch vehicle, you know, you load liquid oxygen and then you have to unload it. We do an inspection. There's cork insulation on the launch vehicle, and it had begun to kind of peel away from the underlying structure.
And so they had to go in there, repair the cork, replace it, until they felt that they had that problem under control. Once that was taken care of, off we went.
When we get to the landing sites on Mars, in order to get to the locations that the scientists are interested in sending the rover, we have to use our engineering expertise about how the rover actually behaves in many tests that we've done here on Earth in order to advise them as to how to get the rovers to those locations safely and reliably.
Our goal, of course, was to design a system that was robust enough to handle anything that Mars could throw at us. But of course, the problem there is we don't know what Mars can throw at us. Mars is a different planet. And so we stretched our minds and our imaginations as far as what it's likely to throw at us, designed the best system that we could to deal with it. But Mars can surprise you. And we need to be knowledgeable enough about the limitations of the system we've created before we land so that we can answer some incredibly hard questions that might come our way about, is that safe to do? Is this safe to go to? How far can we push the system? We did about a week and a half's worth of testing up in the Mars yard on a variable tilt platform that we covered with 6 inches of sand, and we had the rover drive on this deep, loose sand over obstacles on slopes that varied from 0 degrees to 20 degrees. By testing these rovers under much more extreme conditions than we tested the flight rovers, we're finding where their performance boundaries lie.
From a navigator's perspective, the most difficult challenge of getting to Mars is hitting a target at the top of the atmosphere, such that you will land precisely where you want to on the ground. Hitting a target this small is like trying to thread a needle from 15 miles away. Imagine how difficult it is to thread a needle from just this close. Now imagine that we have to start 15 miles back, and we only get 6 opportunities to change our position while trying to thread this needle.
Between launch from Earth and arrival at Mars, we have opportunities for 6 trajectory correction maneuvers, also referred to as TCMs. The first few are really to correct for the trajectory departing the Earth, and the last few, the last 3, trajectory correction maneuvers 4, 5, and 6 are really to fine-tune the flight path to hit the desired target at Mars. So when we do the last nominal trajectory correction maneuver, the spacecraft is approaching Mars, and Mars is also moving through space. So we have the spacecraft moving at about 50,000 miles per hour, and Mars is actually overtaking the spacecraft. It's going faster, about 55,000 miles per hour. So we're trying to hit a target on Mars when we're moving and Mars is moving and Mars is approaching us very fast. So it's a very difficult problem. I mean, we thought things were very busy before launch, but after launch things got much more intense. It's just constant activity and there's no time to stop and take a breather. So at the last nominal maneuver, which is called trajectory correction maneuver number 5, we're still at a distance from Mars that's about 500,000 kilometers, which is about 300,000 miles. So hitting that target from that great a distance is like kicking a really long field goal. If you think of a football game, it's like kicking a field goal from Boston to Philadelphia.
EDL, that stands for Entry, Descent, and Landing. But its main job is to take a vehicle that is streaking across interplanetary space. These speeds that our spacecraft travel are just tremendous, and get those speeds down to practically 0 on the surface of Mars. We have a heat shield, we have a parachute, we have rockets and an airbag. And we have to use all those elements in very quickly and get it all done in 6 terrifying minutes.
Everything we do in EDL is decided by the computer. We have different sensors that trigger different things, and there isn't time to call back and say, hey, the winds are higher than we expected, or you know what, I'm going to hit a big pointy rock that's going to hurt these airbags. It's all about autonomy. I think that's probably, in my mind, the most challenging part. It's just lack of control.
The spacecraft hits the atmosphere of Mars at 12,000 miles an hour. That's time 0 for our entry, descent, and landing sequence.
When we hit the top of the Martian atmosphere, we're moving at a speed of 25 times the speed of sound. That's like 20 times faster than a speeding bullet.
And that atmosphere is thick enough that it's going to turn the front end of that heat shield about as hot as the surface of the sun.
Hot gases have enveloped the spacecraft, and the outside skin of the heat shield will reach a temperature of 1600 degrees Celsius. This lasts for 30 seconds.
There's a huge temperature difference from the inside and the outside of the heat shield. The vehicle on the outside is getting thousands of degrees centigrade, while the inside may get up to barely room temperature.
We go through what's called the heat and deceleration pulses. As it slows down through the supersonic speeds and approaches Mach 2, we open a parachute. We're going now about 1,000 miles an hour.
So that parachute comes out, it really slows the vehicle down really fast, and it brings us from going almost sideways to bringing the whole vehicle almost vertical.
The Mars surface is rapidly approaching. We're still moving now about 250 miles an hour.
20 seconds after we deploy the parachute, the spacecraft has slowed to subsonic. In other words, at this time it's moving slower than the speed of sound. At that point in time, we jettison the heat shield.
And then 15 seconds after that, the lander pops out and rappels down a 20-meter-long bridle, a rope.
So what happens is while the lander is being lowered from the back shell, the whole spacecraft is hanging on this cord here. And it's really about the size of a shoelace. It's not much thicker than that. So when that's done, we've got this really neat system where it's got the parachute on top, the back shell in the middle with the retro rockets, and the lander down below.
At this point in time, the radar will have acquired the surface. It'll be in lock with the surface.
And once it sees the ground with the radar, it figures out how fast it's going and how high it is. From that, it can do the math to figure out how long the rockets need to be on.
We added very late in the project a descent imager. It's a camera that takes 3 pictures and compares high contrast items in those pictures to try to determine the horizontal velocity at which we're moving across the surface to help decide which transverse rockets we're going to fire.
At this point in time, we have to fire the retro rockets or we're going to slam right into the ground.
And just about 5 seconds before we hit the surface of Mars, we inflate the airbags in the lander, then we light the retro rockets. The retro rockets bring the whole system from about 150 miles an hour down to 0, about 15, 20 meters off the surface.
And then we cut the bridle, and the airbag falls the final distance to the surface.
Net velocity when we land is about 24 meters per second when we hit the surface. We hit hard, we bounce high.
Smack, the first impact, 40 Gs. We bounce just as high as we fell from, and then smack again, nearly 40 Gs.
It could kill it right there. The first bounce, if the rocks are in the right formation, if you hit the bags in the right way. Our system isn't bulletproof. It has Achilles heels, and if the rocks want to find those, they can.
And then bam, again and again and again. Some 15 to 30 impacts, each slightly smaller than the previous one, until finally we end our last minute in this rolling, bouncing rollout that terminates with the lander sitting quiet at 0 miles an hour on the surface of Mars. And that's it. MER has landed. EDL is complete.
This is the first time ever that we've had a very sophisticated golf cart-like spacecraft, which is basically put into a cocoon, jammed inside the aeroshell when it goes through the Martian atmosphere, and it has to basically, like a butterfly, go through its metamorphosis before it can do the job for which it was designed.
Normally when you go off and try and design a spacecraft, you try and avoid things like deployments, avoid deployments, avoid motors and actuators, avoid too many pyro devices, We have all of those things that you would normally just try and avoid in the design of your spacecraft because we have to.
It has to be folded up in a kind of a robotic origami. The wheels in front have to be folded in on themselves. The back wheels have to be pulled in. The solar arrays have to be nested up. The high gain antenna and the PanCam mast that you see on here all has to be kind of nested into a very, very compact shape. It is definitely 20 pounds of stuff in a 5-pound bag.
There's a lot that has to happen in the impact to egress phase. In the first day, we fire almost 50 pyros and get the spacecraft reconfiguring. There's the airbag retraction, there's the lander pedal deployment, there's the solar array deployment, there's reconfiguring the power bus, there's getting us into a configuration where the rover is ready to receive commands from Earth. And then at that point, we're in a state where we're collecting data, taking images, and transmitting it to Earth. That's the first day.
There's a combined 36 to 40 actuators that have to do their job. There's tens of pyrotechnic devices that have to do their job, and every one of those things has to be verified in sequence in order for us to feel comfortable with driving the vehicle off onto the surface.
If the airbags don't retract, we could potentially catch the lander when we try to deploy it. If the lander pedals don't open, the rover itself is trapped inside the lander and can't deploy its solar panels. If the solar panels don't deploy, we don't have any power to charge our batteries, which is our only source of power on the surface. So if any one of these doesn't happen, it's a bad day on Mars.
So the second day after the first night where it gets power is it has to make sure that it has good communications with the Earth.
We also can only talk to the Earth when we can see it from Mars. You can think about the sun rising and setting on Earth. Well, the Earth rises and sets on Mars, and we can only see and talk to the Earth when it's above the horizon.
After that, the rover must then stand up, which means it has to get all of its wheels, which are bent down like this, plunged out in all directions, and it has 6 of them. And then it must get away from the lander, and then takes a few pictures to see where it is, and then finally, checking all of its systems to make sure it's okay, it has to say, all right, I'm ready to be on my own. My next thing I have to do is I have to cut all of my electrical connections to the lander. This is a big moment. This is a birth, in truth, because from that moment on, the rover is completely on its own.
If you look at this pocket sitting here, you'll notice that it looks suspiciously like a wheel. And you'll also notice if we grab a wheel, that the wheel will sit very nicely in it. And these are pockets that were deliberately put in because we had to accommodate this wheel sticking outside of this tetrahedron. And these very same pockets and pockets like it are things that we have to be able to drive over and not get caught in. Now these ramps, what they do for us is they give us 3 different ways we can get off of this lander. The reason that they're needed is because when we do land on airbags and in the uncertain terrain, we can end up at tilts so that the entire lander is tilted to the side. We can have it pitched up forward. We can have a combination thereof. So what these ramps are doing for us is they're giving us the capability to go off in different directions and handle terrain that we don't really know is going to be there until we get there.
It might take as many as 10 days to get safely onto the surface. Or if we run into big problems, it could take as long as we need to. It's a process that we don't rush, and we do what's necessary when it's necessary, and we make no risks doing it.
That whole process, which is an exciting week right after landing, is called impact to egress. First time it's ever been done, and based on my experience, it's the most complicated and fascinating engineering sequence ever done on a robotic mission.